Welcome to the session. Good morning, all. This is Dr. Damodar Reddy, Associate Professor, Department of EEE. So, in this session, I would like to discuss about insulated gate bipolar transistor. So, generally, insulated gate bipolar transistor is a three-terminal power switch. So, which is having high input impedance like power MOSFET, and also having high low on-state power loss like BJT. So therefore the best qualities of these two can be incorporated in the IGBT working. So the best qualities are nothing but high input impedance of MOSFET and low on-state power loss of BJT. So both are incorporated in this fabrication of IGBT. Therefore the IGBT is most popular power switch among the power electronics devices or applications. So this is about IGBT best qualities incorporated from the MOSFET and BJT. So here the IGBT is having again the input characteristics like power MOSFET and output characteristics similar to the power BJT. So the symbol, hence the symbol is also as amalgamation of symbols of two parent devices. So the combination merging of P MOSFET and P BJT like power BJT. So we can introduce the IGBT structure or IGBT symbol. So here you can see that IGBT having three terminals similar to the MOSFET, that is we can call gate, emitter and collector. So these three are the switches, and the circuit symbol can be shown in the following slide like no. So we are merging here the MOSFET configuration and BJT configuration. Therefore we can introduce the IGBT symbol. So before going to this, previously the IGBT can be called as metal oxide insulated gate transistor, or you can say MOS IGT, or conductivity modulated field effect transistor, that is COMFET, or you can say gain modulated FET. So and also it was called insulated gate transistor. So these are the different names can be taken for IGBT. So then IGBT is a relatively new device in power electronics, and before the advent of IGBT. So before the introduction of IGBT, so the common use of power switches in the power electronic applications are power MOSFET and BJT. So these both switches are having some kind of advantages and some kind of drawbacks or disadvantages. So when we talk about BJT, power BJT, it is a current control device which is having bad switching performance and low input impedance and also it is having a drawback with the secondary breakdown. So on the other hand, the BJT can exhibit excellent conduction characteristics. Similarly, we can talk about the voltage controlled power MOSFET where it is having excellent switching characteristics and having high input impedance, but also it exhibits a bad conduction characteristics. So with this one more drawback we can discuss here, that is problematic with the parasitic diodes at higher ratings. So before invent of this IGBT into the market or power electronic applications, so we use about power MOSFET and BJT with their best qualities, and these best qualities can be incorporated to manufacture the IGBT. So though the unipolar nature of P MOSFETs leads to low switching times, and it also leads to high on-state resistance as the voltage rating increases. So this is again we can this is the drawback with these MOSFETs. So therefore we can move on to the next power switch, that is called IGBT. So thus so need of such a device which had goodness of both P MOSFET and BJT. Therefore we introduced about MOSFET in the next level. So when come to the construction of MOSFET, so IGBT is on P plus layer constructed on the P plus substrate. So on the P plus substrate, a high resistivity N layer is epitaxially grown. So this we can see in the diagram in the coming slide. So as in other semiconductor devices, the thickness of N minus layer determines the voltage blocking capacity of the IGBT. So if the junction J2, so whenever it is reverse bias, the blocking capacity is very high. So therefore this N minus layer defines the blocking capacity of the voltage. So on the other side of the P plus substrate, a metal layer is deposited to form the collector terminal. So the in the construction, the structure of IGBT indicates that, see, the bottom of CP substrate can be deposited with this collector terminal. So now the P regions are diffused in the epitaxially grown N minus layer. So uh, the electrons or holes pairs can diffuse or drift to the one layer to another layer from P region to the N region. So then further the N plus regions are defined in P regions. So there is a drift and diffusion of the electrons hole pairs takes place, then there is a flow of current in between the collector and emitter terminals. So we can see the basic structure of the IGBT concept. So here we can see the IGBT construction or structure. So this shaded line indicates that metals can be used for all the terminals. So here it is also collector terminal, emitter terminal. So this emitter emitter terminals can be connected together here to get into next level. So next, base is the gate is connected between the uh, collector and emitter. So the base is isolated with the silicon dioxide. So there is no direct connection with the structure of the IGBT with the gate. So gate is isolated with the silicon dioxide. Therefore, so the ions, the negative ions are accumulated at the near to the gate junction, gate terminal, and the positive ions are accumulated to the N plus layer. So with this we can see here the transfer of electrons from P plus to N or N minus, and transfer from collector to the emitter terminals. So this is nothing but whenever, so we give positive of gate with respect to the emitter, so we have to apply some kind of voltage to the between the emitter and gate. Similarly, the collector is positive with respect to the emitter, so therefore we have to apply some external voltage between the collector and emitter. So previously the junction J1 and so J3 will come into forward condition, and the J2 will be in the reverse condition. So this is in the reverse condition. So whenever we apply the forward voltage between the collector and emitter and gate to the emitter, so therefore the junction J2 will be vanish. So then the flow of electrons will be takes place, then current will flow from takes place from the electrons are in the reverse direction from N plus to in the opposite direction to the collector, then current flows from collector to the emitter. So this is about supplying external voltage between the emitter and gate and collector and emitter. So this is about structure of the IGBT. So now we can analyze this structure. So here an insulating layer of silicon dioxide is grown on the surface. So to isolate the gate terminal with the actual structure of the IGBT, so we use the silicon dioxide. So this insulating layer is etched in order to embed metallic emitter and gate terminals. So we can observe in the diagram here. So the insulated gate, the insulated silicon dioxide is embedded here between the gate and emitter terminals. So under the bottom of the at the collector, the P plus substrate is placed which is called injection layer. So because it injects the holes into the n minus layers, the transfer of electrons from p plus to n plus region. So then afterwards the n minus layer is called the drift region, where the next p layer is called the body region. So from the n minus layer the electrons are drifted to the next layer, so therefore we can call it as the drift region. So then p is called the, so this p can be called as the body region and n minus is called as the drift region. So the n layer in between the p place and p region serves to accommodate the depletion layer of p-n junction. So this is general in the reverse direction whenever collector and emitter supply is given. So then after some threshold voltage, that is going to be breakdown. So here we can see the equivalent circuit of IGBT. So the input side of the IGBT can be seems like a MOSFET, and the output side of the IGBT can be seems like a as a transistor, that is p plus n minus p minus PNP transistors. So therefore gate and collector emitter, three terminals, and because of the drift region resistance, we can represent the resistance between the collector and gate. So the approximate equivalent circuit of IGBT comprises of MOSFET and transistors, transistor Q1 in the equivalent circuit. So to account for resistance offered by the n minus drift region, so we can represent RD as been incorporated in this equivalent circuit. So this is again we can represent the same structure of IGBT with detailed information. So this emitter terminals are connected together, and one more is gate, and between the gate and emitter we used to take the positive voltage gate with respect to the cathode, and similarly positive collector with respect to the emitters. So here you can see all the junction J1, J2 and J3. So whenever we apply positive voltage at the collector with respect to the cathode, J1 junction and J3 junction are in forward bias and J2 is in the reverse bias. So whenever we increase increase the emitter collector to emitter voltage, the junction J2 will be vanishes. So this is seems like a transistor, that is two transistor analogy of the thyristor. So this is nothing but the thyristor symbol. So the entire structure of IGBT in the output can be seems like a thyristor, that is NPN transistor and PNP transistors are connected together, so to operate collector to emitter current. So from this we can say that, so as we move up vertically the collector to emitter, so we come across p plus n minus p layers. So this means that IGBT can be thought of as combination of MOSFET and p plus n minus p transistors. So as we seen in the equivalent circuit diagram, so this indicates that input side indicates that MOSFET and output side indicates that p plus n minus p transistors. So therefore, so this is the basic approximate equivalent circuit of the IGBT. Now, so from this structure observation, we can introduce one more equivalent circuit. That is, so there exists a path from collector to emitter. So that path is, we can say, p plus n minus p channel, and one more is n plus and other emitter. So therefore there exists a one more transistor Q2, that is n minus p n plus, that is, so in the structure we can see that there are two transistors, one is n plus p n minus transistor, another one is p and p n minus p plus transistors. So this seems like a thyristor configuration. So this is the exact equivalent circuit of IGBT. So where we can see the current flow from collector to gate and collector to emitter. So these two configuration we can see here. So in this collector, whenever we give a positive voltage with respect to the cathode, sorry, collector positive with respect to the emitter. So then after breakdown voltage, the current flows from collector to emitter. By the time the gate of the Q2 is supplied with this emitter current to operate Q2 switch. At the same time, the current gate current of the Q1 can be transferred to the gate of the input MOSFET. So this is how we are going to operate the exact equivalent circuit of the IGBT switch. So there is a body region resistance in the P region, and there is another resistance called drift region resistance can be represented in this equivalent circuit. So now come to the working principle of IGBT. So in this we can see the working principle of IGBT: biasing of gate to emitter terminals and collector to emitter terminals. So generally we used to give VGE VGE as voltage between the gate to emitter, and VCC between the collector to emitter. So with this positive voltage applications between the terminals, we go with the operation of the working of the IGBT. So when collector is made positive with respect to the emitter, so IGBT gets forward bias. So here also we give a VGE between the gate and emitter. So with no voltage between the gate and emitter, the two junctions between N minus region and P regions, that is J2 is in the reverse bias. So whenever we apply a positive voltage between the positive voltage at collector with respect to the emitter, so then the IGBT switch becomes a forward condition, and the where J1 and J2 will be in the forward bias and J2 is in the reverse bias. So without gate applying any gate to emitter voltage. So after that there is no current flow between the collector to emitter until the gate to emitter voltage is applied. So that means when gate is positive with respect to the emitter by some voltage applied, Vg. So then at the point of VGET, so that is nothing but gate to emitter threshold voltage applied. So the junction J2 is going to be vanished. Then the current flow will be starts from collector to emitter, because already collector to emitter is positive voltage is applied. So then this N channel is called as the inverse layer. So previously in the from the structure you can say this one inverse layer. So this N channel short circuits the N region with the N plus region. Then therefore the electrons flows from N plus emitter begins to flow to the N minus region. So opposite to the electron flow, then we can take the current direction. So that's why it's a inverse layer. So as IGBT is forward bias with the collector positive and emitter negative, so the P plus collector region injects the holes into N minus region. Here you can see from whenever the this is positive with respect to the emitter, this is the emitter minus. So then the drift of our holes from positive substrate to the N minus layers. So this is happening here. So thus N minus drift region is flooded with electrons. So from P body regions, then holes from P plus collector regions. So this is happening between the junction J2. So the injection carrier density in the N drift region increases considerably. Then therefore subsequently the conductivity of N region is enhances. So as we increase the whole electron and hole pairs from P plus to the N minus layer, so then the conductivity of the N region is increased. Therefore IGBT gets into turned on by vanishing the junction J2. So the forward current flows from collector to the emitter. So then the IGBT is, starts conducting in that particular threshold value. So the collector current IC, the collector current IC in the IGBT constitutes of two components, that is IE and IH. So IE is the current due to the injection electrons flowing from collector to the emitter, then through the injection layer, drift layer, and finally reaches to the channel formed. Next one is IH is the whole current flowing from collector to emitter through the Q1 and body resistance RBY. So therefore we can represent the total current flows from collector to emitter is the sum of IE plus IH. So although the IH is almost negligible, therefore we can simply say IC is approximately equal to the IE. So this is a peculiar phenomenon in the observation of IGBT. So therefore we can say latching of IGBT. So these occur when collector current exceeds the certain threshold value ICE. So in the parasitic thyristor gets latched up and the gate terminal loses control over the collector current. Therefore IGBT fails to turn off even when gate potential is reduced to low. So as we see in the thyristor concept, once the thyristor get into turned on, then the gate signal is turned off automatically. But here it cannot be possible in the IGBT, even though there is a potential reduced between the gate to emitter terminal. So the turning off of IGBT is now another circuit, commutation circuit is required here. So it's a forcibly turn off of the IGBT can be takes place like a thyristors. So if device is not turned off as soon as possible, it may get damaged. So once the thyristor is turned on, then current flows from collector to emitters. Then so there is no requirement of gate voltage or gate current to turn on to get in to hold the IGBT into on state. So we can turn off the gate to emitter voltage. So we can observe the characteristics, static characteristics of the IGBT by taking the practical circuit diagram. Here collector to emitter, this IGBT switch. In this we have to limit the current between the current to emitter. We are having the RC resistor here. So then collector is supplied with the positive energy with respect to the emitter. Similarly, the gate is positive with respect to the emitter. So the common point is here emitter. So so from this characteristics we can see that initially there is no current flow in the device, that is from collector to emitter. As we increase the gate to emitter voltage, that is at the junction J2, we are applying positive gate voltage with respect to the cathode. As we increase that voltage, the current starts flowing from 0 to some value, then it reaches to saturation at particular value called breakdown voltage. That is, you can see here the breakdown voltage at particular value of this one. So initially there is no current flows, but only a small current flows due to the minority charge carriers. So by keeping the different values of VGE, we can draw the IC current with respect to the VCE. So that is nothing but this is the voltage VCE. So at constant values of different VGE values, we can take the characteristics between VCE and IC. That means as we increase the voltage between the collector and emitter, the current IC going to be increases, but before particular time there is no current flow because the gate to emitter voltage is not applied. So after getting the gate to emitter voltage, the minority charge carriers becomes majority here to flow the current between the collector and emitter. So therefore we can increase the value of VGE and we can increase the level of voltage flows from collector to emitter. So these are the different voltage levels of VGE. So then the corresponding IC value can be taken, but it will reach us to the saturation after some time. So therefore there is no need of gate to emitter voltage after some time of the battery on state. so so the graph indicates that it's a similar kind of BJT characteristics, except that the parameter which is kept constant for a plot is VGE. So because IGBT is a voltage control device, unlike BJT, because BJT is a current control device, therefore which is a therefore it is similar. So we cannot have VGE constant values in the BJT. So when the device is off state or on off mode, VC is positive and VG is greater than VG is less than VGET. So this is the threshold value between the gate and emitter. So the reverse voltage is blocked by the G2, and when it is reverse biased, so that is VC is negative, then J1 blocks the voltage. So this is about the until 0 to threshold value VGET. So there is no current flow IC. Then after VGET there is a drastic change in the current, that is it rises gradually from 0 to some extent. So the transfer characteristics of IGBT, which is exactly same as the power MOSFET. So the IGBT is in on state only after VG is greater than the threshold value. This is again similar to the power MOSFET characteristics. So now we move on to the switching characteristics of IGBT. So here you can see the voltage applied between the emitter gate and emitter. So initially it is very low value, then it is gradually increases to the level and then saturated. Again the gate value is decreased after a switch is getting into on state. So here we have to talk about three basic things, that is rise time, delay time, and total time of the switch power switch. So here we can with this we can say this is the voltage between the collector to emitter, and this is about current between the collector to emitter increases gradually as we applied the VGE and VCE. So here we can see initially there is no current flow between the collector to emitter, because at low voltage we cannot get the value of IC, but a small current will flow, that is due to the minority charge carriers. So here we can see delay time and rise time, then we can call it as the turn on time. So what is meant by delay time and rise time? So we have to talk about delay time here. So the total turn on time is composed of two components, that is delay time and rise time. So the delay time is defined as the time which collector rises from leakage current due to the minor charge gauges to the 10% of this, it's a final value of the current. So from 0 to its final 10% of its final value reaches in the delay time. At the same time, the voltage between the collector and emitter falls to its final value to the 90%. So during this during this starting period of the switch, so there is a rise time and delay time in the process of turning off IGBT. So next one is the rise time is nothing but the collector current rises from its 10% to the its final value of collector current, and at the same time voltage falls from 90% to the 10% of its final value. So therefore the combination of rise time and delay time can be called as a turn on time of the IGBT switch. So that we can represent here in this area. So the delay time and rise time of the switch. So in the other hand, so there are initial fall time and initial delay time can be represented with the switching characteristics. So that is nothing but the turn off time T off consists of three components: delay time, initial fall time, and final fall time. So the delay time is defined as time taken for the collector current falls from IC to, that is final value, to 90%, and VC is begins to rise. So it's quite opposite to the turn on time. So here the initial fall time is the time during which collector current falls from 90% to its 20% of IC value. At the same time, collector to emitter voltage rises from 10% of its final value to 90%. So this is about the final fall time is defined as the time during which the collector current falls from 20% to the 90% to the 10%, and the voltage, this is 90% to the 10%, and voltage rises from 0.1 or 10% to the its final value. So therefore the sum of values, delayed time and initial fall time and final fall time, can be taken as the turn off time of the switch. Here we can see the duration of the delay time during the turn off, and fall time, and initial fall time and final fall time of the currents and voltages takes place in this switching characteristics. So after that, so what are the advantages of IGBT in the market? That is low gate drive requirements. So here for the commutation process or turning on or turning off of the device, we require the lower gate drive components, and having the lower switching losses, and the small snubber circuit requirement also needed, because protection of the IGBT switch is mandatory. So the snubber circuit is employed for the protection purpose with the combination in parallel to the switch. Then high input impedance, then it will avoid the damage of the switch because of high input impedance, and it's a voltage control device. So controlling is very easy because of external voltage control, external voltage applied to the terminals. So controlling is very easy, and temperature coefficient of on-state resistance is positive, so and less than the MOSFET, hence the less on-state voltage drop. Therefore we get the low power losses in during the on-state of the switch. So and enhanced conduction due to the bipolar nature. So this is conduction characteristics from the BJT can be taken. So that's why it's and one more is better safe operating areas. So generally there are three regions to operate: cutoff region and active region and saturation region. All will be comes in this also similar to the MOSFET. And when we talk about disadvantages, when compared to the other power switches, this is quite costly, and there is a latching up problem with the IGBT structure, and high turn off time compared with the MOSFET. So again here forced commutation methods sometimes used for turning off of the switches, so therefore the turn off time is very high when compared to the other switches. So these are the disadvantages and advantages of IGBT switch, and all the construction point of views and switching characteristics and the structural point of view can be discussed in this session. So thank you.